Behind me I have a graph of a ball rolling across the floor to a stop. It starts traveling at time 0 traveling at 30 meters per second, and at time 24 it has finished rolling to a stop. Now, solving for the acceleration, which we find via the slope of this line, or solving for
the displacement via the area.
is something we do very well. The problem is what if we want to ask other questions, more general questions, such as what is across the first 25 meters? How long does it take to cross the first 25 meters? And suddenly everything we know breaks down. Now, there are several ways we can do this. We could say, well, okay, we can find this area using t as an unknown and solve for it that way. It's messy, but it gets possible. It ends up being a quadratic that we need to solve out. We could solve for the entire area and then solve for this area using the, again, system of equations setup. And at that point, we could find out exactly how long it takes. But again, it ends up with being a quadratic and being very messy and time consuming. What we need to do is generalize the graphical process into equations that we can use that are easier to handle and manipulate than everything else we've been doing. So we're going to start by going through the process of getting these equations using the graphical tools we used in the first unit, and then applying these two practice problems. We'll start with the velocity timeline. Here, we have this line. Getting equations for lines of things we've done. This line specifically will have this thing of y equals mx plus b. Every line has that equation. So let's start by plugging in the easy parts. What is the y measure? What is the x measure? Well, we get those from our units. Looking at the x-axis, we're measuring t, or time. Looking at the y-axis, we're measuring v, or velocity. That just leaves us our slope and our y-intercept. But we know what our slope is. Slope is the slope of a velocity time graph is our acceleration, which leaves my y-intercept, b. Well, at time 0, what's going on? What's happening here? We say that's my initial velocity, or how fast I'm going to go originally. In this case, v naught. Now, this equation is on the equation sheet for AP Physics. First equation on the equation sheet in the top left corner, they put a little extra signifiers for x to indicate that you're moving the x direction, but that's not strictly necessary for right now. It's also directly related to the definition, because if I move this v naught to the other side, I have v minus v naught equals a times t, which is delta v equals a times t. Move the t to the other side, a equals delta v t. Regardless of how you get there, this equation is the definition of acceleration in just a different form. It is the first of what we call the kinematics equations that allow us to solve problems. Let's go ahead and give it a try here. Instead of using the definition, let's plug in. So, I want to know, let's say I want to find the acceleration. Let's start there, somewhere nice and easy. In this case, a is my unknown, it's what I'm solving for. So, v at the end of my graph, how fast am I going? Well, I'm going 0 meters per second. So 0 equals a times 24, because at time 24 seconds, I'm going 0 meters per second, plus the 30 meters per second I was going originally. Solve for a. First things first, subtract the 30 to the other side, negative 30 equals a times 24. A equals negative 6/5. And my units here will be meters per second squared. Double check our answer. Does it make sense? Does it fit with what we see here? Yes. We have a negative downward slope, and it's a little short, not much short, but a little short of being a 1-to-1 ratio. From this, we could go back, solve our equation, and it'd still be a system of equations, but at least we have a little idea. This is how we get our first equation. Let's take a look at our second. The second graph we would look at would look something like this. We'd have an initial velocity, we'd have a final velocity, and we'd have to find the displacement in this case. And how we would do this is we'd take it and we'd split it into a triangle and a rectangle and add their areas together. Now, instead of going through with numbers, let's see if we can't generalize this process. We have two objects here. We have a triangle and the area of a rectangle. Let's find out how each of these work. Rectangle is going to be base times height. How wide, how tall? Well, in this case, it's the same kind of idea as what we did last time. It's just what each side measures as opposed to what each side represents. How wide is the base? How wide is it from here to here? Well, take a look. We're starting from 0. We're going over to this imaginary point, t. So my base is t. Okay, but how tall is it? Well, look back at the previous graph we did. Think back to the previous graph. At this point here, we called this something. We called this our v, but it wasn't just v, it was our initial v, which tends to be designated with this little not symbol. Now, for reasons that we'll get into in a bit, this is typically related as v naught times t, putting the v first. Again, we'll get into the y in a bit. Just trust me for a moment. So we're going to take this value and add it to this value. So now we got to find that value. The area of the triangle is 1/2 times base times height. The base hasn't changed. It's still time. The height, however, is a small problem because it's just this section here. Well, how did we get that? How did we find that? We found first how fast we're going at the end, which we'll call v, and we subtracted off how fast we were going originally, or v naught. So that this height is v minus v naught. But if we think back a step, we can look at this equation up here, equation 1. And we can go through and go, wait a minute, wait a tick, wait a tick. We can make that simpler. So instead of saying v minus v naught, which is totally fair and valid, what we typically say instead is we rearrange equation 1 from v equals v naught plus at to v minus v naught equals at. And so since my height is v minus v naught, what I can do is I can plug in at instead. So my height is at. Simplify that, multiply everything together, you get 1/2 a t squared. Put all that together, and you're going to get delta x equals v naught t, which is the area of your rectangle, plus 1/2 at squared. For the AP exam, the way they write this on the equation sheet is they break the delta x up. X equals x naught plus v naught t plus 1/2 at squared. They're going to write this as this. And there we go. So There's your second kinematics equation. Second one on the sheet, second one down. Problem is the third one. The third one is a combination of the two of these run through algebra. I don't feel like going through the algebra is particularly helpful, but if you want to, there will be an extra video posted going through the algebra. The important thing of that is that the third equation is this. So if you combine these two, equation 1 plus equation 2, you can get an equation where you don't need t to solve. These are the three kinematic equations they give you on the AP exam. I use and will give one more, but that's the derivation of these three equations.